Okay, good morning everybody. We are starting in on nuclear magnetic resonance today. This is based on the same technology that's used for MRIs. And there's a ton of physics involved in this, most of which we will ignore. One of the great things about nuclear magnetic resonance is you don't have to know how it works in order to be able to use the data. And that's great. I want to give you enough of the background physics that you sort of know what we're talking about. So to begin, you know that electrons have a quantum property called spin. You can think of it as an electron spinning around on its axis, though that picture is not actually what's going on. The electron's a point charge, it doesn't spin, but it acts as though it does. And of course, a spinning charge, a charge moving in a circular motion, generates a magnetic field. Well, that's the same way with protons and neutrons as well. They both have characteristic properties called spin, and that spin generates a magnetic moment. So, for example, a single proton with spin is a little magnet and has a little magnetic field. So you would expect all hydrogen atoms to have some ability to sense and or respond to a magnetic field, and they do. But it's not just limited to hydrogen atoms. Other nuclei have combinations of protons and neutrons. And there's this whole elaborate thing called nuclear shell theory, or the nuclear shell model, that you can use to predict whether or not a nucleus should have net spin. Of course, in most organic molecules that you've seen, the electrons don't have net spin because the electrons come in pairs, one with upspin, the other with downspin, and overall spin is zero. There are molecules, which we'll talk about in chapter 21, that have one unpaired electron or even two unpaired electrons. Oxygen, actually, molecular oxygen that we breathe, has two unpaired electrons. Those molecules can respond to magnetic fields in interesting ways. In the same way, proton and neutron spins come in pairs. It's more complicated than that. But the net effect is that if your molecule has an odd number of protons, that is an odd atomic number, like hydrogen, or if it has an odd mass number, that is an odd total number of protons and neutrons, it should have a net magnetic moment, should have net spin. I'm never going to ask you, does this isotope have net spin? You're never going to have to figure that out. People have already done that. But the point is that there are a lot of nuclei that we are interested in organic molecules that respond to a magnetic field. So hydrogen has an odd mass number. And yeah. I did not do that. How long has it been that way? The whole time? Seriously, you guys sat there for 5 minutes? You're very patient and you're very kind. Thank you. Well, that should be better. You see it now? I was recording the whole time, though, so. Well, you can see it. There's your little spinning proton. Got it? Good. Okay. Nuclei with odd mass numbers and odd atomic numbers have net spin. So just look at some of the things that are on the list. Hydrogen, carbon, that covers most of the stuff that's in organic molecules. Fluorine, phosphorus, nitrogen. Some of these, and especially, you don't need to know this really, but nuclei can have spin numbers that are 1/2 or 1 or 3/2 or so on. It's not worth really knowing at this level, but the nuclei that are easiest to analyze are those that have spin 1/2. And this includes a lot of things that we're interested in organic chemistry. So proton that has net 1/2 spin is almost 100% abundant. That means we'll be able to sense protons in all organic molecules. C13, only 1%. So our experiments with C13 are going to be less sensitive because there's fewer carbon atoms in a structure that are NMR active. N15 is another one that's interesting, but again, not very abundant. Fluorine and phosphorus, on the other hand, highly abundant, and we can do experiments on those too. In this class, we will focus mostly on proton NMR. We will do a little bit with carbon NMR. If you want to do or learn more about these, you can you should talk to Dr. Scott Burt, who runs our NMR facility, and he'd be happy to tell you more about that. And some of our experiments that we do in OChem involve some of these nuclei. So with that, that's all the physics background you're going to get. You good? Protons, some nuclei are magnets. Right. Now, magnets respond to magnetic fields. So in the absence of an external magnetic field, the nuclei, individual magnetic moments are randomly oriented. But when you apply an external magnetic field, and if the field is strong enough, we're using B naught from physics to indicate an external magnetic field that we apply. A magnetic field is a vector, it's in this direction. There are two states that an individual nucleus can adopt. It can either align itself with the magnetic field or against the magnetic field. Either of those options is okay. Being aligned with the field is slightly lower in energy than being aligned against the magnetic field. And anytime there's an energy difference, there's some kind of spectroscopy we can use to measure that energy difference. So to illustrate that, here's a nucleus in an external magnetic field, and here are two energy states. The lower energy one is where we're aligned with the magnetic field, the higher energy one where we're aligned against the magnetic field. This energy difference is related to how strong the field is. Magnetic fields are measured in Tesla or Gauss, but Tesla is more common. We don't mean the vehicle, we mean that's a unit of magnetic field, so named for Nikola Tesla. 14.1 Tesla is a common magnetic field strength. If you get, that's strong enough of a magnetic field that if you walk close to an instrument that has this level of magnetic field, you can feel the keys in your pocket move. And if you get even a little bit closer, it's going to start to erase memory if you have magnetic field-based memory on your, not your brain, gosh. No, we're talking about electronic memory, yeah. Credit cards, other things like that. You're like, this class suddenly got way more interesting. Yeah. So you do have to be careful around these instruments. The field is strong enough that it can pull metal out of your hands. So when you approach one of these instruments, it's important that you not have any magnetic metal on you. And downstairs where we have these instruments, there's these circles painted on the floor that indicate, hey, don't come in here if you've got keys in your pocket. However, despite how strong that field is, this energy difference is still very small. This is orders of magnitude away. So the energy difference is 5 times 10 to the minus 5 kilocalories per mole. That's 1,000,000 times or 10 million times weaker, about 1,000,000 times weaker than, no, I'm sorry, I'm thinking. About 20 million times weaker than a carbon-carbon bond. So this is a minuscule amount of energy. And it's an energy difference such that at room temperature, you'd basically expect 50% of the nuclei to be in the lower energy state and about 50% to be in the higher energy state. However, photons, because of the relationship delta E equals h nu, where nu is frequency, we can calculate the frequency of photon that would allow, could be absorbed and allow a nucleus to transition from this lower energy state to the slightly higher energy state, and that's in the radio frequency. So IR spectroscopy, if you remember, was in the 10 to the I'm going to have to look. What did we say? 10 to the 14 hertz or something like that. Scroll up. Yeah, 10 to the 14, 10 to the 15 hertz. Now we're orders of magnitude lower than that in the radio frequency in the megahertz range. So whereas infrared spectroscopy was exciting transitions among vibrational modes in a molecule, NMR spectroscopy is looking at much, much, much lower energy transitions. But this experiment is still pretty easy to do. So if all, go ahead.
I'm just having trouble reading that. Is that microhertz or megahertz?
Megahertz, sorry, yes. I think that's intentional, that our letter M resembles the Greek letter mu, whatever. All right. Maybe I've stood too close to the spectrometer. Maybe I couldn't remember. I don't know. Okay, so if all protons absorbed at the same frequency, this would be a very boring experiment and we wouldn't be doing it. It turns out that the frequency at which a nucleus absorbs and can undergo this transition is highly sensitive to its environment. And therefore, we can learn things about a proton's environment, that is its surroundings, what is it connected to, from the frequency at which it absorbs. In addition, the shape of we're going to get a spectrum that shows which frequencies are absorbed for a given sample, and there will be peaks in that spectrum that correspond to different kinds of protons. And the shape and the size of those peaks is going to tell us a lot about the connectivity of the organic molecule. For the most part, at the beginning, we're going to be doing this just for protons. But even though we're just looking at protons, the information we get from the spectrum will basically tell us most of what we need to know for the carbon-hydrogen and carbon-carbon bond connectivity for an organic molecule. So this is a really, really powerful technique. So what is this strange device which can erase credit card strips, but not your memory? It looks like this. I mean, if you're squinting and looking at it at the side, it looks kind of like a Star Wars moisture evaporator from Tatooine, crossed with maybe a Gonk energy droid and maybe R2-D2. Is that enough Star Wars references obscure for you today? The sample goes in a tube that's through the center of this device. Your sample is held in a little glass tube, and then this collar allows it to sit inside the spectrometer, and the sample is spun around to help with signal averaging. That's beyond the scope of what you want to do. Most of this is a really powerful superconducting electromagnet. It's kept cool with, this is like a giant thermos with multiple levels inside. There's a liquid nitrogen level, and then inside that there's a liquid helium level. The liquid helium cools the superconducting coils of the electromagnet. You charge it once, and then it's good to go. The electrons continue to cycle, and you create a magnetic field. The field lines correspond to this central shaft that's in the middle of the spectrometer, and so your sample sits in this external magnetic field. And then there's some stuff not shown here that surrounds your sample, coils, it's called a probe, but it shoots in radio frequency radiation and then measures stuff from the sample. There's a big box of electronics that's required to translate what goes on inside the instrument into the NMR spectrum that you get on the computer. And these range in size. As I said, the spectrometers we have in our department, the field is strong enough so that the frequency that most protons absorb near is around 600 megahertz. There are early spectrometers where only 60 megahertz. There are some that are 300. If you go to a major research institution at places that have like medical schools where they do a lot of high-level research, they will have spectrometers that are in the gigahertz region, maybe 1 gigahertz. And the idea is the stronger the field is, the actually more sensitive and the better resolution the instrument gives you. That's maybe more details than you need to know, but that's what it looks like. Let's talk about the NMR spectrum. This is the NMR spectrum for methyl tert-butyl ether, which is, I think, an additive in some gasoline. You've got a methyl group, a T-butyl group, and an oxygen. On the x-axis is frequency. Similar to IR, it's tradition to show it low to high, right to left. So low frequency over here, high frequency over here. Now you'll notice that the frequency is given not with the Greek letter nu, or is it mu? No. I know that this is mu, but this is nu. Is it nu, like mu is? No. Whatever. Okay. This is the Greek letter nu. It's not V, it's nu, and it's for frequency. But notice that frequency is not given in that in those units. It's given in weird units of chemical shift, and we want to talk about what that means. By the way, since we're on a Greek letter kick, the chemical shift term is symbol is going to be the Greek letter delta, which we use for tons of stuff, and this is just another one. Okay, so frequencies vary from around 600 megahertz to around 600,006,000 hertz. So it's sort of inconvenient to label axes like that, right? Because you just have too many digits. And so what we do to control for that is we calculate chemical shift. We say, all right, what's the range of useful frequencies? It's about 6,000 hertz. So we're just going to call this 0. We'll pick a reference frequency. So this is the reference frequency. And then whatever frequency we're at here, we're going to subtract the reference frequency from that. So say at this point, 600,006,000 hertz minus 600 million hertz, we get 6,000 hertz. That number is still too big to be convenient to plot on an axis. So we're going to divide it by our reference frequency. Only at this point, instead of dividing it by if we divided it by 600 million hertz, we would have a decimal, which is also inconvenient to display. So instead, we're going to divide it by 600 megahertz. So we'll have 6,000 hertz divided by 600 megahertz. We get a nice number 10. And then hertz cancels. We've got mega in the denominator, which means we got a factor of 10 to the minus 6, which we call parts per million. Those are our new units. And there we go. That's mostly background. I'm never going to ask you to do that math, but if you want to know there is a direct connection between chemical shift in ppm or parts per million and frequency. Lower chemical shift is lower frequency. Higher chemical shift is higher frequency. Okay, questions about that? All right, and it's all relative to some reference frequency. A common reference compound is tetramethylsilane. You see one peak here. It's got 12 protons. They're all identical. You see one peak, and that's at a frequency that's decently far removed from all of the other organic, where all the other protons might show up in an organic molecule, so it's useful as a reference and it's not going to interfere with anything. All right, let's talk about the spectrum a little bit more. Just to orient you, higher values of frequency for historical reasons only are called downfield. I don't know why. Okay. Whereas lower values of frequency are called upfield. There is a reason for that. It no longer matters, but you will probably in the text and in some problems you'll have to deal with, they'll talk about, oh, well, what about that peak that's downfield of this other peak? And you just need to know that downfield is to the left at higher frequency, upfield is to the right at lower frequency. Okay, a couple of other things to notice. This spectrum only has two signals in it, two peaks. We'll talk about what is meant by an NMR signal. One of the peaks corresponds to the tert-butyl protons, and the other peak corresponds to the methyl protons. They have different environments. There is a reason that the methyl protons show up downfield of the tert-butyl protons. We'll talk about that. There's also a reason that the tert-butyl protons have a higher intensity than the methyl protons. We'll definitely talk about that. By the way, when I say peak intensity, I don't necessarily mean peak height, I mean area under the peak. Those are two slightly different things. You can think about them as basically equivalent for our purposes. Okay, questions so far? Yes?
So the thing on the far right that is upfield, I guess.
Yes.
So it says this TMS reference. They just have like a blank that they put into the...
It's a great question. So do you just put in a blank beforehand? You can. The other thing sometimes you do is you just spike your sample with a little bit of TMS. Yeah, you just add a little bit. You don't have to. Not everybody does it. There are other ways around it, but that's been traditional. Okay, good. Others? All right. So what do we mean by NMR signal? An NMR signal is a peak or a cluster of peaks that come from a single proton or a group of identical protons. This is a really important principle for NMR. Identical protons show up with the same NMR signal. This is why we only see one signal for this methyl group, because the 3 protons of the methyl group are identical. And this is why we only see one signal for the 9 protons of the tert-butyl group, because they are all identical too. So in order to interpret NMR spectra accurately and correctly, we're going to need to figure out how do I know if protons are identical or different. Fortunately, a lot of what you've learned in Chapter 5 from stereochemistry should be really helpful to you here, but I'm going to review. So there are 2 different ways to tell if protons are identical or different. One of them involves symmetry. The other involves a kind of strange thought experiment. I like the symmetry method better, so we're going to talk about that first, then we'll do the strange thought experiment. So, before we talk too much about the symmetry method, I need to remind you of what are called symmetry operations. There are 2 of them that will be relevant here. One is called a CN axis of rotation, where n, we'll talk about what n is, and then the other is a mirror plane operation. So a rotational axis, here is BH3, it's trigonal planar. BH3 has multiple rotational axes of symmetry. One of them, if we think about these 4 atoms all being in the same plane, one axis of symmetry is perpendicular to that plane and goes through the boron. And it's a C3 axis because if you rotate around the axis by 360 divided by 3, which is 120, it's what's called a 3-fold axis of symmetry. If you rotate by 120 degrees, the protons are interchanged in their positions, but the molecule is the same. Okay? Questions about that? Similarly, there are several C2 axes of symmetry in BH3. One of them is aligned along this BH bond. If I rotate around that axis by 360 divided by 2, or 180 degrees, the 2 protons here and here swap their positions, but the molecule's unchanged. Okay? Then mirror planes you should be pretty used to. Here are the various mirror planes that BH3 has. One of them is in the plane of all of the atoms. That's sort of the boring one. One of those planes is aligned with this BH bond such that the wedge proton and the dash proton are reflections of each other. If a mirror plane can interchange 2 protons but the molecule is unchanged, those 2 protons are identical. And here are a couple other mirror planes of symmetry. So that's an example of groups. We would say that the 3 protons of BH3 are identical and that they show up with one NMR signal. Just not to belabor the point, here's a couple other situations you see in organic chemistry. A methyl group, CH3 attached to something else. That methyl group has a 3-fold axis of symmetry. If you rotate by 120 degrees, the protons swap places, but the molecule's identical. There are also mirror planes for the methyl group. Here's one of them. If you align the mirror plane with the bonds in purple, this CH bond and the CY bond, the wedge and the dash protons are reflections of each other. Finally, if you look at a CH2 group that's attached to 2 other things, there's no rotational axis of symmetry, but there is a mirror plane. If you align it with these 2 bonds, the proton in the front and the proton in the back are reflections of each other. Okay, so that's a crash course in rotational symmetry and mirror symmetry. You got to think about both of them. Now, what kinds of groups are identical? Protons that are interconvertible by a rotational axis of symmetry are always identical. They are called homotopic for same shape. They are always identical. They always have the same NMR signal. So here are some examples. These 2 protons, HA and HB, in propane have a C2 rotational axis of symmetry, so they are homotopic. They are always, always identical, and they will always show a single NMR signal. What's true for protons can be true for groups as well. So take a look at this larger molecule, a 5-membered ring. You've got a methyl group that's a wedge and a methyl group that's a dash. You have benzene rings here abbreviated as phenyl groups. One is a wedge, the other is a dash. There is a C2 axis of symmetry here. If you rotate 180 degrees about this axis, the phenyl group C goes to the place where phenyl group D is and vice versa. And methyl group A goes to where methyl group B is and vice versa. Because that C2 axis interchanges these 2 methyl groups, those 2 methyl groups are identical to each other. Now we already know that the protons of a methyl group are identical to each other as well because of what I showed you here. So that means that if I looked at an NMR spectrum from this molecule, I would expect to see one peak for these 6 protons, one signal rather for these 6 protons. Similarly, I would be able to see that these benzene rings are identical to each other. Okay, that seems obvious. Let's now talk about a slightly different kind of situation where protons are identical almost always. So protons that are interconvertible by a mirror plane, not a rotational axis, but a mirror plane, are what we call enantiotopic. You hear that term, enantio? It sounds like enantiomer. That's not a coincidence. Okay? Enantiomer referred to 2 molecules that are mirror images of each other. Enantiotopic groups are 2 groups that are mirror images of each other. Enantiotopic groups are identical except in a chiral environment. I'm adding that exception because it's important in biology. It's not really going to be important for this class as we analyze NMR spectra. Here's some examples of enantiotopic protons. Here's ethanol. Proton A and proton B are not interchangeable by a rotational axis, but the mirror plane shows you that protons A and B are mirror images of each other. They are enantiotopic. They are identical except in a chiral environment. What I'm saying is an enzyme, say liver alcohol dehydrogenase, would be able to tell the difference. An enzyme is chiral. An enzyme would be able to tell the difference between proton A and proton B. But in the absence of a chiral environment, they're totally identical. Okay. Similarly, this can be what's true for protons, can be true for groups as well. Here is a mesodiol. you can see there is a mirror plane that says that methyl group D is the reflection of methyl group C, OHF is the reflection of OHE, and proton A is the reflection of proton B. Protons A and B are enantiotopic. OH groups E and F are enantiotopic. Methyl groups D and C are enantiotopic. They are identical except in a chiral environment. Yes?
What do you mean by chiral environment?
Chiral environment would be in an enzyme active site. So enzymes are chiral, and in an active site of a chiral molecule, you could tell the difference between these groups.
So it doesn't have to do with the molecule itself being chiral?
No, because the molecule itself is not chiral. Nevertheless, in a chiral environment, you could tell the difference between those groups. Yeah. Okay, good. Other questions? So you might wonder, why should I bother learning the difference between homotopic and enantiotopic protons? The distinction is subtle, and if you forget it, it's probably okay. But it actually is going to come up in the 353 organic lab that you're going to deal with. And I probably will ask an exam question on whether protons are homotopic or enantiotopic, because I feel like it does push you on symmetry, and that is a useful skill for you to continue to maintain. Okay, so finally, we have protons that can't be interchanged by any symmetry operation. Protons that can't be interchanged by a rotational axis or by a mirror are just different, always, no matter what. And if those two protons or two groups are attached to the same carbon, we have a word for that which we call diastereotopic. That's an interesting word and a challenging concept. This one's difficult to illustrate just based on symmetry operations. So we'll talk about a second method for determining whether groups are diastereotopic. Here's some examples. This molecule is 2-butanol, and it has a stereocenter, which I'll illustrate with by labeling it. That's the stereocenter. Two protons in a chiral molecule on a two CH2 protons in a chiral molecule are diastereotopic. There's no mirror plane that can reflect A into B because this stereocenter breaks the symmetry, right? Do you see how, as we've drawn it, A is on the same side of the molecule as the OH, but B is not? And no matter what you do to rotate around this carbon-carbon bond, A and B are going to see this carbon differently. So A and B are always different. Because they are on the same carbon but are still different, we call them diastereotopic. Here's an example of diastereotopic groups. Here is a molecule with a stereocenter. Here are two methyl groups attached to the same carbon. You would normally think, oh, they're identical, but there's no rotational axis of symmetry that interchanges the two. There's also no mirror plane that interchanges the two. One good way to look for groups that are diastereotopic is two of the same type of atom or group attached to the same carbon in a molecule that is chiral. Okay, so I think the symmetry method is really great for identifying homotopic and enantiotopic groups. Remember, homotopic groups are always identical, even in a chiral environment, and enantiotopic groups are identical except in a chiral environment. Diastereotopic groups are just always different. Now, method 2, which your text takes you through, and I don't want to spend too much time on it, is to determine whether two groups are identical or not. You do a thought experiment where you replace one of them with something that's not a proton, say just Z, whatever Z is. Then you draw that. and then you draw another molecule, and again, this is just a thought experiment where you replace the other proton with Z, and you compare the two and see, are they the same or are they different? So, for example, for homotopic groups, let's take propane. We already know that A and B are homotopic. This thought experiment replaces A with Z to generate this molecule, which I'm calling A. Then we replace HB with Z to generate this molecule, which I'm calling B. And then we compare molecules A and B. And in this case, a pancake flip shows you that they are identical. Okay? If you do this thought experiment and the two replacement molecules are identical, the groups are homotopic. Okay, probably easier to see that just with symmetry instead of doing the thought experiment. You can do this with enantiotopic groups as well. Here is ethanol, that example I gave you before. We already know that A and B are enantiotopic because they are reflections of each other through a mirror plane. If we replace proton A with the Z group, we don't even have to say what Z is, it's just not proton, it's different. We get molecule A. If we replace HB with the Z group, we get molecule B. Now compare A and B, these pretend molecules we've done through this thought experiment. What's the relationship between those two? Enantiomers. Therefore, if the thought experiment gives you enantiomers, the two protons you replaced are enantiotopic. Okay? And they are the same except in a chiral environment. Now, this last one may be the most useful example of the thought experiment. If you want to know if two protons are diastereotopic, protons A and B in a molecule that already has a stereocenter, replace proton A with the Z group, draw that, now we've got molecule A. Replace proton B with the Z group, now we've got molecule B. Compare those two molecules. What's the relationship? Diastereomers. You can tell that because the one stereocenter stays the same, the other stereocenter changes configuration. So the thought experiment molecules are diastereomers, therefore the protons we replaced are diastereotopic. All right. That's important because interpreting the NMR spectrum is much easier when you have realistic expectations. That is, when you know how many different kinds of protons a molecule has. So, now we're going to practice. How many kinds of different protons does a molecule have? Oops. There we go. When you're first doing this, it can be useful to draw in the protons that are implied, but sometimes not shown, because after all, the NMR experiment senses protons. So, take a look at that. Tell me these two protons on this CH2 group. Homotopic, enantiotopic, or diastereotopic? Remember, homotopic, you look for a rotational axis of symmetry. Enantiotopic, you look for a mirror plane that interchanges the protons. Diastereotopic, you do the thought experiment. These two protons, A and B, identical or different? I'll write down your options: homotopic, enantiotopic, or diastereotopic. Anybody willing to commit yet? The stakes are low. Go ahead. You say enantiotopic. Why? Good. If you do the thought experiment, they would be enantiomers. So the thought experiment looks like this. We'll put an R for the rest of the molecule. Put Z for proton A, or Z for proton B. Do the thought experiment, those two are enantiomers, therefore they're enantiotopic. Good. The other way to do this is what? What's the mirror plane that exchanges protons A and B? It's just the plane of the page, right? B is going back into the page, away from you. A is coming out in front of you. The mirror plane is the page and exchanges those two protons, okay? So that is right. These two are enantiotopic, which means they are identical, unless of course we're in a chiral environment, but for the most part we won't be, so they're identical. Okay? What about the other CH2 groups? What about these two protons? Are they the same or different? They're the same. They're different from these. Good. You can tell they're different because they're in an entirely different environment. There's no symmetry operation that will trade protons C and D with protons A and B. So you're right. C and D are distinct from A and B, but what's the relationship between C and D, with D, the relationship between those two protons with each other? They're enantiotopic, good. So I have a set of protons here that are identical to each other. These two are identical. Same argument, these two are identical. What would you say about the methyl protons? Homotopic, enantiotopic, or diastereotopic? Homotopic. You got the rotational axis of symmetry that exchanges the protons on the methyl group. So these, these are, oh, I need a highlighter, not a pen. Well, whatever. The methyl groups are homotopic. Okay. All right, let's do a slightly different one. Okay, first I want you to answer the question, how many different kinds of protons do I have? And then we'll deal with, as we identify groups of protons, we'll deal with this issue of homotopic and antiotopic and so on. Okay, I'll give you a minute or two to think through that. Let me give you a hint really quickly. Remember resonance with the benzene ring. And taking resonance into account when dealing with symmetry is important. I could just as easily have put the double bonds like this, right? If we draw the resonance hybrid, the bond between, what I mean is that if we number carbons 1, 2, 3, 4, 5, and 6, that the bonds between 1 and 2 should be the same as the bond between 1 and 6, if that makes sense. Okay? All right, what have you got so far? Number, anybody want to commit to number of different protons?
4.
Go ahead.
6.
4, 6, 5, somewhere in there? Okay. Somewhere between 4 and 6. Good. So tell me one group of identical protons. The methyl on the end is identical to, so those 3 protons are identical to each other. Good. What else? Oh, on the other end. So you're saying that these 3 are identical to those 3, okay? We would say that the methyl proton itself, those 3 protons are homotopic to each other. These 2 mirror images of each other and antiotopic. Okay? Good. What else? The CH3 on the top is its own thing. Those 3 are identical to each other. They are homotopic to each other. Good. Not identical to anything else in the molecule. Okay, what else? That's 2. What, say that again, sorry? The one hydrogen at the bottom, he's his own thing, right? Not identical to any other proton in the molecule. Okay, others? Those 2 here, interchangeable by... Oh, I didn't see that. Actually, yeah. I told you that these protons are mirror images of each other, which they are, and they're an antiotopic, but they're also exchangeable by, do you see the C2 axis? It's right here. So that would mean that these 2 protons are actually, the methyl protons are actually homotopic. Yeah. I mean, we would come to the same conclusion if we called them an antiotopic, that they're identical. But if you find the C2 axis, that means they're homotopic. Good. Okay. How about the CH2 protons? So relative to each other, those 2 CH2 protons are enantiotopic. They're mirror images. But by that rotational axis, we can exchange the ones on the left with the ones on the right. My right, my left, not yours. And so we would say these 2 groups are, the 2 CH2 groups are homotopic. Okay, good. It can get a little bit trickier when you start introducing rings to molecules, but you are right, there are 6. 1, 2, 3, 4, 5. No? Did I find 5 or is that 6? 1, 2, 3, 4, 5. Yep, 5 different kinds of protons. 5 different kinds of protons, 5 different, we would expect 5 different NMR signals for this molecule. Okay, what about this? How many different kinds of protons in cyclopropane? 1 and only 1. Do you see any mirror planes? Tons, right? There's one in the plane of the page. There's another mirror plane here. There's another one there. There's another one there. Do you see any rotational axes? One right through the middle of the page, perpendicular to the page. Spin around 120 degrees and the protons are interchanged. So yeah, we would say that there's only one kind of proton in this molecule. All right, I want to leave you with just one thing for you to work on. It's an example that's in your chapter, but try it first before you read the answer. I'm going to replace one of those groups with something that's not a hydrogen. That changes things. Now I want you to figure out how many different kinds of protons are in that molecule. All right, and that's where we will stop today. I will see you Friday.